Hello, I'm Albert Ruthera, and I'm a computer system architect and computational engineer at the Lincoln Laboratory Supercomputing Center and the MIT SuperCloud team. In this section, we are going to discuss the application software categories that are installed on high-performance computing systems. In discussing the categories, I'll mention some examples of software applications and packages that are part of each of the categories, and some of them may be familiar to you. We cannot discuss HPC systems without talking about the software packages and applications that are installed for users to solve their simulation and data analysis projects. As one should expect, HPC systems have compilers and libraries installed for Fortran, C, and C++ codes that are utilized by scientific simulation applications. This also includes one or more versions of the ubiquitous Message Passing Interface Library, or MPI. MPI is a rich library for passing messages between processes and between compute nodes within a parallel job running on a cluster. There are a variety of open source and commercial versions of MPI that have been developed, refined, and optimized over the past several decades, including MPICH, ENVAPICH, OpenMPI, Intel MPI, and Cray MPI. For decades, HPC codes have been developed, updated, and optimized in these languages and libraries. Some codes have gone through many such cycles over several decades, and they are as robust and even more accurate than their first iterations. Alongside the compilers and libraries for Fortran, C, and C++ are parallel debuggers and performance analysis tools. Parallel debuggers, including TotalView, DDT, and Parallel Application Debugger, allow programmers to execute their programs in parallel while monitoring variable values, setting breakpoints, and deeply evaluating failure modes. Performance analysis tools such as vTune, Amplifier, MPI Analyzer, and Valgrind enable programmers to determine what part of their code result in slow execution. More recently, high productivity languages have emerged to make data analysis and rapid prototyping more efficient. These high productivity languages include MATLAB, GNU Octave, Julia, Python, and Java. Their development environments have gained a great deal of usage because the code is compiled as it is executed, which is also called interpreted code. And they perform well for many different rapid prototyping and data analysis activities. Further, there are many toolkits and software libraries that package high-level functionality so that code prototypes can be programmed effectively and quickly. Such toolkits include a wide range of technical areas including software-defined radio, astronomy, satellite propagation, and robot sensor fusion. Very recently, machine learning training has migrated to using high-performance computing systems because machine learning training is very computationally intense as neural network models and training datasets become larger and larger. Many HPC systems now offer a variety of machine learning frameworks including TensorFlow, Caffe, PyTorch, Keras, and Spark. The installation and dependencies between all of these frameworks are managed by the Anaconda software management tool. All of these use Python to some degree to manage machine learning data structures and parameters, which means that rich Python environments are also installed. Not all applications are run on HPC systems are developed in-house. Not all applications that are run on HPC systems are developed in-house. Most HPC systems also have a variety of third-party and commercial software packages. Examples of these are computational fluid dynamics codes like Fluent, electromagnetic simulation codes like FECO, material science analysis code tools like XCRIS-SDEN, weather simulation software like WRF, which stands for Weather Research and Forecasting, and chromosome DNA alignment and matching tools like BLAST. Finally, some HPC systems also have high-performance databases like Accumulo and SciDB installed for advanced data management and analysis work. These two databases are built for high-performance data management for scientific applications. SciDB is an array-oriented database which can be scaled up to many server hosts. Its basic data building block is an array of data, and it is especially good at storing and computing on time series signals and arrays. The Accumulo database is a highly scalable key value store that can handle dynamic database schema to manage data. In that capacity, it can store and compute analytics and data structures such as graphs and unstructured and/or dynamic databases. Each supercomputing center has different users with different software needs. However, you will find that these categories span all of the software needs, and there are many commonalities among all of the needs across supercomputing centers.